Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing Chapter 6 on nonparametric methods, discussing paired data, and then more generally, nonparametric methods with in one sample tests, comparing them to T-tests and understanding when it would be most appropriate to use each and what are the advantages and disadvantages. So let's go back to a paired data situation where we have sleep remedies. We've seen this in a previous chapter, chapter 3, I believe, on two sample tests. And we've got two sets of sleep remedies, remedy A and remedy B. And for each person, we have their improved sleep over an undrugged night of sleep. So for this first person, sleep remedy A gave them 0.7 hours additional sleep, and under sleep remedy B they had almost 2 extra hours. And the paired difference here of B minus A will be how much additional sleep do you get under sleep remedy B than sleep remedy A, a comparison of the sleep remedies. If we ask the question, are the data normal, and that's not a question we need to ask for a T-test. Recall, we're interested in the whether the sampling distribution of the mean is normal, and we can use the bootstrap to assess that. But anyway, let's see if the data themselves are normal. The Shapiro-Wilks test suggests that the data are not normal. If we look at a plot of the data, we observe actually that the data are fairly symmetric in the center, but we have two extreme values to the right and to the left that suggest the data are not normal. And that's probably what the Shapiro-Wilks test is indicating when it says it's not normal. In particular, this right point is drawing the gray diamond in the center out to the right. Now just 10 seconds of comments about this plot. At the end, I've used this function coord flip to flip the axes, the x and y axes. So all the labels that you see, initially the x-axis is labeled with just a character D, and the y-axis is the data themselves for D. We have a y-intercept at 0, and so on, and all those things happen, and then the coordinate flips puts the plot horizontally. And this is really handy, especially when you want to save room on a page. This plot isn't any more informative when it's vertical than horizontal, and we save a lot of space by going horizontal. All right, so let's scroll down a little bit more. Oh, yes, and take a look at the T-test versus the Wilcox sign rank test. So here, a T-test, right, we're assuming that the sampling distribution of the mean is normal. We're testing whether the difference between the sleep remedies is 0, and we find that there is a statistically significant difference, and that, in fact, the confidence interval for the difference between the two sleep remedies goes from 0.6 to 2.4. All right. Wilcox sign rank test, recall, assumes symmetric data. And when we look at the plot, we don't see symmetry here that well, but we know from the procedure of the sign rank procedure that we're going to look at the ranks of the data. And so these last two values, the first and the last, the minimum and maximum value, get assigned the rank of 1 and 8. I think there's 8 observations here. 2, 4, 6, 8, 10. 10 observations, excuse me. So rank 1 and rank 10, sort of regardless of where they are. And so visually, actually, the center of this data doesn't look very far from symmetric, especially given a small sample size. And so I'd be willing to accept the assumptions of symmetry for the sake of the Wilcox test. We specify that the mean or median equals 0, and we actually have a very similar result to the T-test, 0.008 versus 0.004 for the p-value, and the confidence interval also not that different, 0.8 to 2.8 compared to 0.6 to 2.4. All right. So one of those cases where we don't have difference in inference based on the model that we use. Now, some comments on using nonparametric methods. When we have symmetric distributions, the means and medians are approximately equal, and in those cases we can use the Ttest, the sign test, or the Wilcox procedures for tests and confidence intervals under that situation. Now, when we don't have that situation, say we've got extremely skewed data, then the sampling distribution of the mean is unlikely to be normal. We don't have symmetric distributions for the Wilcox test, and so the sign test is going to be the one that we'll be able to use. And we'll be able to get confidence intervals or conduct tests for the median even under very skewed distributions or one with lots of extreme outliers. Now, alternatively, we've seen in the past that we can transform the data. So if you got right skewed data and you transform, maybe you get a symmetric or roughly normal distribution on the transformed scale, in which case we can then use those t-tests or t-confidence intervals again, remembering that all the inference is on the log scale. So we're no longer estimating the mean of the distribution, but the mean of the log of that of the distribution. All right. When we have those normality assumptions met, then the t-test and t-interval are going to be the optimal tests. It's going to give us the narrowest confidence intervals and the most powerful hypothesis tests among all other procedures to test for means or construct confidence intervals. When you've got heavy-tailed symmetric distributions, so something that's sort of peaked in the center, but then to either edge goes out for a long time, where we have extreme observations to the left and to the right. So it's sort of an unusual distribution. If you look up double exponential distribution, you'll see an example of this. Then the t-test and t-interval tend to be conservative, meaning because we have those extreme observations to the left and to the right, it's going to inflate the standard error of the mean, because it's also inflating the standard deviation of the sample. And that's going to make the confidence intervals wider. It's going to make the test procedures have larger p-values than we'd like them to have. And so that is called, in this case, a robustness to validity, in that even when you have large standard deviations, it typically isn't going to cause a big problem for the t-test when you have this, when you still have symmetry. All right, but what does happen is that we end up having a large effect on sensitivity of the t-test and the confidence interval, meaning that yes, we have intervals that are way too wide and p-values that are way too big. And so this is an example where, because of outliers and inflation of the standard deviations, where nonparametric methods actually perform much better than the t-test or t-intervals. So let's see an example of that shortly. Let's see, then I see. I'm going to get to that in a moment, to that example. All right. The main point I want to make is that even though not all scientific disciplines have really embraced nonparametric methods, from my observation, primarily because they haven't been exposed to them or don't understand them, they really ought to be used more often than they are. In my scientific work and consulting, I use nonparametric methods almost all the time, whether it's a permutation test or the examples that we've given in this chapter, or a bootstrap version of a test. I'm using nonparametrics all the time because it gives me a way to test whether my inference depends on model assumptions say normality model assumptions. It also allows me to conduct inference when those assumptions are violated. All right. So scientists in some disciplines continue to use T-methods because they believe the methods are robust to non-normality. And that is not always true. That's why we use the bootstrap to verify that normality assumption. And when it is not met, then we know we should abandon it and do something else. There are cases when, right, because of the central limit theorem, when the data themselves can be skewed, but the bootstrap sampling distribution is fairly symmetric and normal. That is the robustness, because the central limit theorem is helping us out. Okay. As noted above, this is a robustness of validity, but not sensitivity. This misconception is unfortunate and results in the routine use of methods that are less powerful than non-parametric techniques. We'll see this below in a second. Scientists need to be flexible and adapt their tools to the problem at hand rather than use the same tool indiscriminately. I see this regularly, and it really bothers me when scientists or other people are using standard classical statistical methods to solve a problem and never check the model assumptions to see whether they're valid. It's really an issue, and people make bad decisions because they don't understand the tools they're using. All right. Non-parametric methods are not a way to cheat in some way. In fact, they're excellent tools and should be used quite regularly. All right. So the only real weakness of non-parametric methods is they don't all easily generalize to complex modeling problems. And there are methods that can be extended pretty well, and some of them require a lot of computation, and we'll see some more of that as we go through this chapter. All right. So let's see. We'll take a break from this video, and we'll come back and look at two sample procedures, and then on to analysis of variance and permutation tests.